I will start with pointing to this man. He's trying to pull the secure water rabbit out of the hat. Maybe I'm trying to do the same. We will see. The key question is, how can we try to promote more sustainable solutions in urban water systems? I will have my main focus on the urban water cycle. And that has two dimensions to this question. The first one is, what are then the key principles in more sustainable solutions or systems? And the second dimension is, how can we analyze and towards making decisions on this? So if sustainability is then the question, I made this word cloud yesterday from the words in my manuscript. Of course, it's quite fuzzy. If you go to the literature and try to find out what does the water research and the water sector include when they would like to see sustainability adapted to water systems, of course, they would focus the triple bottom line, meaning that you have the environmental, economic, and social sustainability. But in order to make sustainability more, let's say, more direct, meaningful to them as water utilities, because they are the ones who are taking the decisions, they would have to access also, or to address also some more practical issues. And they come to immediately the sustainability of assets and the sustainability of governance. So it's the asset management and the governance processes. We are involved in our department. I'm representing then, together with some of my colleagues, a research activity in a European research project called TRUST. So this includes more than 20 partners from different countries. And we started by trying to ask the question, what does it look like, a sustainability assessment framework when applied to water systems? And as you see, I mean, this slide is quite hopeless. You cannot read it. It's too much information. And maybe that's the fact. But after all, what you can see is that you are trying to, okay, you can think of you are feeding the assessment with data from below. That would be data on the current situation, on the trends, on future, let's say, development, paths, possible solutions. And so then for each of those possible solutions, alternatives or scenarios, you would have to examine to what extent do they, each of them, satisfy different sustainability criteria. And there is an outer circle here with altogether 23 objectives and criteria. And they relate to 5 sustainability dimensions. It's the economic, social, environmental sustainability, and the asset sustainability, and the governance sustainability. So this is important. When you then ask, how can you, in a practical process towards decision making, relate to all that information? Of course, it's a multi-criteria problem that we have. Not necessarily optimization problem, but certainly towards making informed decisions. So here you can see just a simple way of structuring over time, where you can compare different scenarios, or you can compare alternatives with respect to each of the criteria that you decide to select, the ones you think for your system are important. And of course, the previous slide showed a large number of criteria, not necessarily all of them are important. And then you would have to, instead of making very sophisticated scientific assessments, you would have to decide what is the good level, what is the acceptable level, and what is the not acceptable level. And then you would say the good level, that's green, the acceptable is yellow, and the not acceptable is the red. This method will also develop in a parallel European Union project called AWARE. So that is what we have to relate to. What are then common criteria today? Well, if we look at urban water systems, we heard previous speakers telling about the problems in different parts of the world, and of course addressing, as was it, the neglected world. Of course, there you have water access. It's the reliable access to water that is the main problem, and the water quality. But also we talk about water pollution, we talk about water blockages, flooding problems, and so on. So it's more the functional aspects of the water systems. What are the criteria that may become, or we see already today, are becoming more important? Not necessarily more important than the previous one, but they have increased importance. It's water safety, it is climate change, both climate change mitigation and adapting to climate changes locally. It's energy, of course. It's toxicity, and it's the life cycle aspects, the life cycle environmental performance, and resource recovery. And of course, some places, water scarcity is dominating. So how can you then use that information and try to apply it? Let's say looking for solutions and try to sort out different solutions. Well, what does industrial ecology deliver here? First of all, industrial ecology, since that is a field of science where you get inspiration from nature and you try to mimic nature in how you develop and design man-made systems, we could say that we have certain design criteria that industrial ecology could offer. First, we are looking for systems to be cyclic. They should use renewable resources. They should, as it said in red here, have low emissions, high recovery rates, and they should be diverse in their solutions so that they are resilient to changes. If you look at those objectives and ask to what extent are they actually then implemented in today's urban water systems, the water supply and sanitation, I would say they are hardly implemented. Some places you find it. Professor Ødegaard will, I guess, point to some system strategies where you could find some of these things. But this represents it's a shift of paradigm of thinking. And in order to get the water utility and decision makers first accept, recognize, and then invest in these solutions, you would need to document that they are cost-benefit effective in the long run. So you would have to document their benefits. And that's also where industrial ecology can contribute. Because industrial ecology has a toolbox of methods available. This shows the generic system definition of an urban water systems. From the left, from the water source, towards the right, to the demand, that are different than consumers, requiring water of different quantity and quality, and then to the far right, to the recipient. And this is normally a linear flow. And then we added to that system by purpose a system at bottom, which is including the cyclic water recovery opportunities. So we have integrated water systems, more local, rainwater harvesting and greywater treatment and so on. These systems or solutions we see become more and more important. They should be addressed and they should be analyzed. And then we added also by purpose on the top of the system a process where you could have resource recovery. You would like to recover energy. Maybe some of the systems could generate energy. You would like to recover resources and nutrients from the water. So therefore, if you are going then to analyze in a long-term perspective one city with respect to its water services, how that is performing, let's say in a sustainability context, from an industrial ecology point of view, then you have to start to fill the diagram with what are the technologies and the assets that you have as part of each of the subsystems. And that technology and assets will mobilize. It will pull on inflow resources, chemicals, energy, materials, and it will push on wastes and emissions, byproducts, emissions to air, and pollutants to water. And that metabolism is the one that is actually then in the end giving the environmental impacts. So if we are concerned about, for instance, the environmental impacts to climate change, to acidification, to eutrophication, or if we are concerned about the costs in a life cycle perspective, this is what we have to analyze and to document. We use this approach now in our research in many different ways. We would examine cities in different countries and look at different aspects. I don't have the time to show you too many things. I will focus on one issue, and that is the so-called water energy carbon nexus, meaning you can think of a mass balance between the water flows and the energy requirement and the emissions related to that, and in a life cycle context, so that you have some direct and you have some indirect flows. And this Sankey diagram shows the results as calculated for the city of Oslo in 2006. Of course, you can do that for any city and for any year if you have the data. What you can see is that the blue part here, that's the water balance, dominated by the stormwater flows downstream. But you can also see that there is quite significant water leakages. Actually, Oslo doesn't know what is the magnitude of the leakages, something in the order of 30%. We are investing quite a lot, money, materials, chemicals, energy, in the treatment and supply of water, and then it's just leaking out. We can also see there is no cycling of water. It's just a linear. And then in the bottom, where you see the energy, you can see the different mix of energies. There is some electricity, there is a little bit of diesel for the operation and maintenance of the network, and the transportation of the chemicals and so on. And there is an in-house generation of biogas from the wastewater facility that is reused. And then at the top you can see from where and how large are the greenhouse gas emissions. So with that kind of information, I think we could ask some questions. It is, okay, if you open up each of these elements of the system, why are the consumption of, in this case, energy, and the emissions, in this case, greenhouse gases, why are they as large as they are? What are the potentials for improving that situation by applying new technologies and new solutions? And what are the difficulties in implementing that? There will be barriers, of course, practical, social, economic barriers. So this is the question that, and the series of, let's say, steps that you would have to include. Also, we did, with a master thesis last year, a comparison of Oslo and the city of Nantes in France. The top two figures here shows the energy consumption for the whole water cycle, from the source, water supply, water treatment, water distribution, not the water consumption and the energy you are using in-house. That is excluded. And then the energy downstreams in the wastewater, stormwater collection, and the wastewater treatment. And it's striking, there is quite large differences here. On a cubic meter basis, Oslo is more, let's call it, efficient. Oslo uses less energy per cubic meter than Nantes. But on a per capita basis, it's totally opposite. Why? So in this case, it's because Oslo has a large leakage of water, and also Oslo has a more intense, more advanced and energy-intensive wastewater treatment process, of course, which it gives benefits to the water that is discharged to the recipient, but it consumes much more energy on a per capita basis. At the bottom, you can also see that there are large differences in the energy. Oslo has a wastewater treatment plant with biogas and with heat recovery. Nantes does not have that, consumes much more electricity, which is also more dirty than the Nordic or the Norwegian electricity, and it consumes some fossil fuels. So of course, this is important with respect to greenhouse gas emissions. When looking then at the consequence of this with respect to one of the dimensions of sustainability, which is greenhouse gas emissions and global warming, we can see the same pattern as for energy. But also quite interesting is that when you look at the life cycle, let's say, origins of the greenhouse gas emissions, at the bottom you see the brown yellow part of the bar there. That explains the indirect emissions, the emissions that you had somewhere else in the system related to production of chemicals and production of electricity. And that's 70%. It's more or less the same value for Nantes and Oslo. So therefore, it tells us that it is important to analyze different alternatives by a systematic and holistic method that includes the whole life cycle. So what could we conclude? Well, first of all, I could conclude that sustainability of urban water systems is a quite multifaceted task. It's fairly challenging. In order to make that exercise meaningful, we have to make it useful to those who are taking decisions, because after all, it's just a basis to inform decision making. Maybe if we would like to rank in terms of priorities the different dimensions of sustainability, the social aspects would be the top priority due to the value of the water, which was clearly demonstrated in previous presentations. And that's important everywhere, all over the world. And the second priority would be the economic efficiency, in order to have at an affordable cost, acceptable cost, but also then to include a cost analysis that actually combines the cost for the individual, the water utility, and society, internalizing the external costs of pollution, for instance. And then finally, of course, you would then look to the environmental impacts and try to focus resource recovery and low emissions in a life cycle context. I could also conclude that when applying this, we see that industrial ecology, which is a science trying to analyze the system's perspectives here, can be successfully applied. We have actually just started doing that on urban water systems, but we see some interesting results. And that can be, of course, advanced in the future. We see that the mass balance approach, the life cycle analysis, is advantageous. And we also see that a structured way to assess this with a metabolism model concept is something that brings us forward. However, as it said in the bottom, actually we don't need to do all those sophisticated scientific experiments. On one side, we know quite a lot already. We know quite a lot on how to act. But also we know that decision makers, if they would like to invest large money, they would have to know that these investments are meaningful and efficient in the long run. And we have some of the methods for that. I will end by showing this nice photo. It's the aqueduct of the Free Waters in Lisbon. I stayed in Lisbon for 2 years, 2 years ago, for 1 year. And that photo reminds me of, in the old centuries, the importance and the visibility of investments in water. Today, maybe the systems that we have, buried underground more or less, are not that visible, but they are equally important. Thank you very much for your attention.